Because I'm taking one left next to one. That's required for a major.
All right.
I think I have two.
I will.
I'm really excited.
I will begin with a word of prayer. So, dear Heavenly Father, we thank you for this day. I thank you for these students. Just ask again that you just bless our work today. Help us to glorify you, what we do, Lord. In your name I pray, Lord Jesus. Amen. All right. So, you guys have any questions? Yes, sir.
Could you give an example of differentiating dy dx out of the polar?
Well, I just say it again.
Is there a way to find the dy dx in the polar without the variance?
Without what?
Like finding the dy dx from the r d theta.
Oh, okay. Okay. So the question is, how do you find dy dx given r equals to some function of theta, right? So I think the straightforward answer to that is to say, well, x is equal to f of theta cosine theta, and y is equal to f of theta sine theta, right? So dy dx at theta is going to be dx d theta, dy d theta divided by dx d theta, where those are understood to be derivatives of what I have above. So like, for example, if I was looking at, I don't know, r equals to, say theta cubed, then I would have x equals to theta cubed cosine theta, y equals to theta cubed sine theta. So then dy dx would be, dd theta of theta cubed sine theta divided by dd theta of theta cubed cosine theta. And you know how that works out, 3 theta squared sine theta plus theta cubed cosine theta divided by 3 theta squared cosine theta minus theta cubed sine theta. And you can calculate d squared y dx squared by the same ideas. Basically, just if you have a polar graph, your parameter is the angle. So just think of using parametric formulas with t equal to theta. But of course, everything has to run through x equals to r cosine theta and y equals to r sine theta. That's kind of the bridge, if you will. Other questions? All right. So then, question. If we consider minus pi less than or equal to x less than or equal to pi, and f of x, let's say equal to x squared. Actually, forget about the x squared for a moment. Let's just say f of x. Piecewise continuous on this interval. How would you find how would you select a sub 0, a sub 1, a sub 2, dot 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 dot, and b sub 1, b sub 2, dot 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 dot, such that f of x is equal to a sub 0 plus the sum n equals 1 to infinity of a sub n. I better just a second here. Sure, I'll mess up my notation. Yeah. Sum n equals 1 to infinity, parentheses, a sub n cosine of nx plus b sub n sine of nx. Stupid example. F of x equals to 3 plus sine x minus cosine of 2x. You tell me, what would I choose for A and for B? I said, you guys, what'd you say? A sub 0 is what? 3. A sub, let's see here. A sub what is that? A sub 2 equal to what? Negative 1, right? A sub n equals to 0 else, right? For n not equal to 0 or 2, that there's none of those. Right? And we just have one non-zero b, namely what? b1, coefficient is 1, and b sub n is equal to 0 for n not equal to 1. So, stupid case, if my function is literally just a sum of sines and cosines, game over, we can just read it off, right? But what if your function's not just a stupid sum of sines and cosines? How would you go about finding these coefficients, these a sub 0s and b sub 0s? So let me point out something to you. We can calculate an integral. I'll do it over here, actually. I'll do it over here. What is the integral from minus pi to pi of sine of nx times the sine of, let's say, kx dx? Did we have this homework problem earlier? Did we ever calculate this? I don't know. Maybe not. We did learn a product formula for sine. What was it? You guys are going to have to help me out. Fine, I'll have to, you're going to make me rederive it, aren't you? Let's see here. So if we have sine of A, sine of B, that's 1 over 2i e to the ia minus e to the minus ia, 1 over 2i e to the ib minus e to the minus ib. Multiply that thing out, I get minus 1/4 e to the I a plus b plus e to the minus I a plus b minus e to the I a minus b plus e to the minus I a minus b, parentheses here. And so if you tilt your head and squint, you can see that that's 1/2 of cosine of a minus b minus the cosine of a plus b, I believe. Let me double check my formula. If I put a and b both equal to pi over 4, right, then what would a, that'd be 1 over root 2, 1 over 2. I should get a half on the left-hand side. And if I put a and b both pi over 4, what do I get? I get pi over 2, which is giving me cosine of 0. Pi over 4 minus pi over 4 is 0, which gives me cosine of 0, which is 1, times a half. 1/2 equals 1/2. Either I'm unlucky or this is correct. So using that here, we've got what? 1/2 parentheses cosine of what? You got yourself a n minus k times x, right? Minus the cosine of n plus k times x, all right? Dx. And you guys can do that integral, right? 1 over 2 times n minus k sine of n minus k x minus 1 over 2 times n plus k sine of n plus k times x. Take all of that, evaluate from minus pi to pi, what you get? While you guys are figuring that out, we differentiate this thing with respect to a. I get cos a sine b 1/2 minus 1/2 sine of a minus b plus sine of a plus b. So my identity for that is 1/2 sine of a plus b minus the sine of a minus b. So guys, what did this work out to? Anybody see it? So when you plug in pi into x, you get sine of a multiple of pi, right? When you plug in minus pi, both of the terms give you a sine of a multiple of pi. But the sine of any integer multiple of pi is? Nobody knows? 0. Okay, good. Whew. All right. Now this is 0. What is the one thing keeping me from saying that without qualification? What is the like 3 things we look out for in math, right? Square root of a negative number, log of a negative number. What's the other thing? Division by 0. When would you get division by 0 here? If n and k were equal or negatives, right? So if we assume that n and k are positive, which is kind of our interest, so if we assume that n and k are, elements of the natural numbers, and we need n to be not equal to k for this calculation to go, what happens when n equals to k? What do you have when you have sine of nx times sine of nx? How's that go? We don't need all this highfalutin product junk over there. That's a sine squared integral. We know that. We expect that on the final. We would be ashamed of Dr. Cook if he did not put an integral of sine squared on the final, or cosine squared. I mean, that's going to be there, right? It's like a law of calculus 2. The integral of sine or cosine squared will be on the final. It's guaranteed. I think you could go back and look at every final exam I'd ever given in calculus 2. You'd find integral of cosine squared or sine squared there. It's got to be there. Not knowing the integral of sine squared or cosine squared on the final of calculus 2, it's a way of communicating to the professor that you just don't care. But you guys care, so you will get that if I was to ask that. So how do you do this? How should we do this? You guys tell me, right? 1/2? Yeah, 1/2 what? 2nx. Yeah, that's it now. Now, it's been a while since we've done this, so it's understandable if you don't know it at the moment, but do make sure you know it by the time we get to the final, right? Okay? Now this we can integrate, right? So what happens? You get yourself x over 2, evaluated from minus pi to pi, and this piece, again, integrates to 0. Let me not write it out, because it's going to give you a sine of a multiples of pi. It gives you sines of multiples of pi again. So that term drops out. Only the half is actually interesting. And what's it give us? Pi over 2 minus pi over 2, right? Which is equal to pi. So let me shorten this story a bit. We could keep doing these calculations, all right? It's very similar calculations, but what you can show through calculations, just like the ones I've done, are three basic identities. Namely that the integral of the sine of nx times the sine of kx dx from minus pi to pi is equal to pi times the Kronecker delta n comma k, like that. Likewise, the integral from minus pi to pi of cosine of nx times the cosine of kx dx is also equal to pi times the Kronecker delta n comma k. I got to be careful here. But that's for n. That's for n greater than or equal to. These are both for n comma k greater than or equal to 1, right? See here how to say this. Now this, you guys, I should probably tell you what that is, right? Kronecker delta n comma k is a nice symbol. What it means is 1 if n is equal to k, and 0 if n is not equal to k. This is called the Kronecker delta. You'll see this as you go on if you take more math. The Kronecker delta. Yes, sir.
When you put that identity, is that supposed to be cosine A sine B or cosine A cosine B?
Which one are we talking about?
In the purple.
In the purple? So what I did was I took this identity up here and I differentiated it with respect to A.
Okay.
So if I differentiate with respect to A holding B fixed, my cosine becomes minus, and my take the derivative of the inside function, the derivative of A minus B with respect to A is just 1, so I just end up with a minus sine of A minus B. And then over here the minus becomes a plus because the derivative of cosine is sine. And so that's where that came from. And then I just flipped the order because, you know. Anyway, that is exactly what you'd need to use to show the following thing. The integral from minus pi to pi of sine of nx cosine of kx dx, this is equal to 0. And this is for n in the natural numbers and k equals to 0, 1, 2, da 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 da, whatever. So, all right. Do you guys know anything else that satisfies this like Kronecker delta pattern? Yeah?
You can use factorial to do that.
Factorial. Factorial. Oof. I don't know. Interesting. How about this? So you guys know about vectors, right? A little bit. Some of you know more if you're in physics. Let's talk about two-dimensional vectors for just a second, right? You've got A, right? A1, A2. How can I select, well, how about this? If I have x hat with x hat, what do I get? So, I mean, this is my notation for 1, 0, 1, 0. What's the, my bad. I'm so sorry. I'm teaching another class where we use that notation. It's messing with my head at the moment. Dot product, right? X hat dot x hat is what? That's 1, 0 dot 1, 0. How's that work out? It's 1, right? What's x hat dot y hat? Right? Likewise, y hat dot x hat. These are the unit vectors. You might use I and j if you're in like Professor Dromby's physics class, all right? Just the unit vectors in the Cartesian directions, respectively. See, these are the dot products, right? You can formulate, you can say all of this concisely as follows. You can say x sub I dot x hat sub j is equal to Kronecker delta ij. This says 1 if I equals to j, 0 if I is not equal to j. So the dot products. And so what I mean here, of course my notation is just x hat 1 is x hat 2 is y hat, all right? My point to you is that the pattern of the integrals of sine and cosine is the same in a sense. But there's a pi instead of a 1, right? But it's kind of like that, right? How do you calculate a1 and a2 using dot products? Well, the way you do that is to take the dot product with the unit vector. See this? A dot x1 hat is a1, a2 dot 1, 0, which is equal to a1. A dot x2, x hat 2, likewise is equal to a2. So you see, I can select the components of a vector by taking dot products. And if you actually work out the mechanics of that explicitly, the reason this works is because x1 hat dot x2 hat is 0. So that piece of the vector dies, and you're just left with the projection onto the first. We can achieve something very similar. Ooh. My bad. Austin. We needed Austin today. Oh well. It's okay. Lost all my Austins. Rest in peace. Hopefully not. They're not. There's a rather famous mathematician who would refer to people as dead if they stopped doing math. Like if they retired from math and ceased doing math, he would just refer to them as if they were dead.
That's the same as that piece, though.
That's the same as that piece? That's funny. I got no jokes today, Sasser. I'm sorry.
No, it's not you.
Oh, okay.
It's me.
Oh. I once had the Pauls get divorced. You know, Somber Paul and Crazy Paul. And I was not there. There was some fight. I don't even know what it was about. But then they refused to be in each other's presence for like 6 months. They had shared custody of me. It was truly horrible. It was like, it was bad. It was bad. All right, so my point to you, and this is kind of a jump, is that thanks. That the dot products over, that we're just going over, in some sense, are like integrations. And because we have these rules for the integral, we can integrate this, and in so doing, we can select just one component as we desire. For example, if I integrate from minus pi to pi of f of x dx, and I integrate from minus pi to pi of this stuff over here, what's going to happen? Well, we worked out some of it, and you'll trust me for the rest of it. What happens to the integrals? So like the integral from minus pi to pi of this piece, 0. The integral from minus pi to pi of all of these, 0. What survives? We just get integral from minus pi to pi of a sub 0, right? Which is also known as, well, dx, of course. So that gives us 2 pi a sub 0. Looks like we just found a formula for a sub 0. A sub 0, apparently, is 1 over 2 pi, the integral from minus pi to pi, f of x dx. So here, integration from minus pi to pi, in some sense, is playing the same role as the dot product for vectors. Okay, so next up, it requires a little bit more imagination. I'm going to have to, well, I guess I want to erase that. But what I want to do is think about what would the integral from minus pi to pi of f of x times, oh, let's say, cosine of, I'll use a j, jx dx. What would that look like? So what I'm going to do is I'm just going to take the thing I'm about to box in red, all right, this right here, and I'm going to multiply both sides by cosine of jx, all right? Multiply both sides by cosine of jx. That puts I got an a sub 0 cosine of jx, right? Plus the sum n equals 1 to infinity of, what do we got? A sub n cosine of nx cosine of jx plus b sub n cosine of jx sine of nx close parentheses dx. So what happens this time? As you calculate these integrals, most of them are 0, right? So this integrates to 0, and this piece over here integrates to 0, right? But let me write out the middle one. We have plus the sum, n equals 1 to infinity. I'll bring the integral inside. We have a sub n, the integral from minus pi to pi, cosine of nx, cosine of jx, dx. But we could work out that that's actually equal to what? This thing right here, right? How's it go? Remember, this is pi times the Kronecker delta of n comma j, which is just a fancy way of saying it's almost always 0, right? It's almost always 0. Where is it non-zero? n equals to j. Now notice that j here is fixed but arbitrary because I multiplied by cosine, right? The n is being summed over. It's a dummy variable summation. So the j should survive. So what we get is pi times a sub j.
Did you repeat that about j?
Yeah, so the j here is fixed but arbitrary. I multiply both sides by cosine of jx. So that means I should expect a j in the formula. In contrast, the n is like a dummy variable of summation. So it's not free. It's a notation for this infinite sum. So I don't expect the n should be my final formula because n is inextricably linked to this infinite sum. No sum, no n. But this Kronecker delta is the natural enemy of the summation. It takes a summation and it makes it into a single term because this is always 0 except for when n equals to j. So I just put n equals to j and I get my pi, so pi a sub j. And looks like I just found a formula for a sub j, right? So if you'll let me, yowzers. I'm going to write it as n instead of j if you guys don't mind. A sub n is 1 over pi, integral from minus pi to pi of f of x cosine of nx dx. So there is the analog of my dot product formula for two-dimensional vector. If I want to select the a sub n, I take the integral with the cosine nx. What do you think I'm going to do next? Well, we also want to know the b's, right? So how do we figure out the b sub n's? So next, I will multiply by, let's say, sine of jx. And it will integrate from minus pi to pi of f of x times the sine of jx. Integral from minus pi to pi of this whole rigmarole up here. A0 sine, I've actually got to multiply through by my sine of jx. If you see the pattern here, you'll start to realize half of the stuff, well, 2/3 of the stuff I'm writing down here. They're just going to go away. Aw, man. Poor planning on my part. Let me erase the previous. Oh, okay, good. If the camera had still been on the other board, it would have been sad at that point. But anyway, so what happens? We've done this dance before, right? I mean, the integral, when we integrate the sine over minus pi to pi, that's a multiple of periods of sine. It integrates to 0. This integrates to 0 by virtue of that claim over there, which you could easily work out in like a homework. If I haven't given it as a homework or math battle problem before, it wouldn't be surprising to see it in the next one. This right here, how's this integrate? This integrates to pi, Kronecker delta, n comma j. Right? So all of this works out to simply b sub j times pi, right? And so we get our third and final formula, b sub n is 1 over pi, integral from minus pi to pi, f of x sine of nx dx. Any questions? Yeah.
So what is the purpose of this?
Ah. Well, so there was a calculus book that came out in about 1780 or so, and it starts out with Lagrange saying every function is a power series. Like Lagrange laid this down, he said, think about an arbitrary function, and he said f of x is equal to like f0 plus f1 times x plus f2 times x squared plus f3 times x cubed and so forth and so on. So basically, you know, in 1780 there's a book come out, something like that, that basically put down the idea that every single function was a power series, right? But then other people were like, hey, hold on a second. Not everything's power series. Power series are continuous, but we also know about functions which are piecewise continuous, right? So something's missing. Now Lagrange wrote that book in part to try to address like lingering uncertainties, if you will, gaps in the foundations of calculus. See, we've been doing calculus since about 1650 to about 1660 to 1800. Calculus was being done, but it didn't have a rigorous footing. All of the things you did in last semester with limits were not known at that time. Not really. People referred to things called fluxions or infinitesimals that were not rigorously defined. All attempts to rigorously define them involved sort of hand-wavy arguments that didn't quite hold up. Lagrange actually offered like a giant like prize for somebody to do it carefully. No one could do it. It prompted him to write this book, which then people found holes in his approach, right? So then there are other problems that people have been trying to solve during this whole period of time, like the wave equation, you know, like waves on a string, or if you have heat and it's flowing through a solid, if you study the flow of heat, it's called the heat equation. And the methods that people like Euler and others used to solve these kind of problems involved taking infinite sums of trigonometric functions, like this. This is called a Fourier series. So a sum of sines and cosines. This is, you know, we talked about Taylor series, there's a power series, a sum of power functions. This is the next step in that story, which is a Fourier series, a sum of sines and cosines. So what Fourier said in about 1805 or so was that you could write any function as a Fourier series. And it turns out he's probably a little bit more right than Lagrange, because the Fourier series covers a much wider class of functions, because it can do things like create a function which is, well, engineers care about this, like, hey, we're on the second floor, aren't we? So check this out. I can't do this on the 4th floor. But that is a square wave, right? On, off, on, off, on, off. Electrical engineers like to talk about these things because it's switching, right? Can you do that with a Taylor polynomial? Yes, but not really. Not nicely. It's very bad. But with Fourier series, it's pretty natural. Anything that's periodic, if you use a sum of sines and cosines, you can pick up the periodicity. And I mean, anyway, it works. These formulas I just wrote down for you, the so-called Fourier coefficients, you can actually find sums of sines and cosines to create a step function like that without much trouble. So let's take this out for a spin. Let's actually find the Fourier expansion for a specific formula. Because I think, you know, so you like, yeah, 10-10. Woohoo. All right. I was like, is class over? No, we have 10 more minutes. Woo. So to answer your question, I thought, you know, this is a good Calculus 2 class, and I was lazy when I wrote the syllabus here, so I should add a topic. So here we are. What? No? Okay. Well, I don't have to? But I've done this much, we should at least work an example. So let's look at f of, will this be on the, yeah, sure, I can put on test phone. Since you asked. F of x equals to x squared. Listen, everything I'm teaching you right now is there is a online supplement to Stewart's Calculus. This is all at the level of Calculus 2. You see that, right? I mean, and the interesting thing is, where the rubber hits the road, it's all Calculus 2. Let's see how that happens. Let's see what I'm talking about. F of x equals to x squared. Let's find the Fourier coefficients. So first of all, what's a sub 0? 1 over 2 pi, integral from minus pi to pi. Now I will say that the careful analysis of the Fourier, the convergence and divergence of Fourier series, that is past the level of Calculus 2. The convergence and divergence theory for these functions is more subtle. All right, I don't mean to make light of that. How do you can do this integral, right? What do you got? What, x cubed over 3, evaluate from minus pi to pi, what we got? So what did you guys get? Oh, it's not 0.
Negative 5 squared over 6. That's squared over 3. Yeah. That's squared over 3. Yeah.
So this works out to pi squared over 3, you say?
Yeah.
All right, I hope you're right. Oh, and to give a better answer to your question, you know, this is interesting because Fourier analysis is a major part of signals and systems for engineering, so it's good for you guys to see it. I got one. Oh, stink. Oh, man. It's not wrong. It's just I was supposed to, well, it's too late. It's fine. Let's go on. What's this? So we got, what did you guys tell me, pi over 3 for the first one? pi squared over 3. All right, great. For, what's a sub n? Integral from minus pi to pi. Well, we got x squared, cosine of nx, dx. Don't forget about my 1 over pi, right? Somebody want to do this? You guys are all working too hard. It's much easier than that. What? No integration by parts here. No.
0 pi.
Why?
I said 3 answers. I don't know.
Which one?
0.
0 is a good choice. The answer is 0. Why is that? Sine is an odd function. X squared is an even function. In total, this is an odd function. If you integrate an odd function about a symmetric interval of the origin, it's 0. You guys need to know this, because the evil professor who's teaching you has a habit of putting questions which test if you know this in a way which is unpleasant if you don't know this, right? Because if you don't know that, you could try to integrate something that you should not be trying to integrate, right? This is something that's important. The integral of an odd function over a symmetric interval of the origin, 0. Now, unfortunately, this one over here, we can't do that because we have an even function. There's nothing. I mean, you could, if it's even, we can double the integral though, right? Let's do that. That's nice. It's much nicer to deal with 0 than with minus pi and pi, right? So our opening move here, let's say 2 over pi, integral from 0 to pi of x squared cosine of nx. Now, you guys, I will buy your, what did you say, integration by parts? Totally agree. dv1, u1, so what do we got? We got our 2 over pi, u1, so what's the integral of this? We get what? X squared, 1 over n, cosine, sine, right? Sine of nx, right? You got to evaluate that thing from 0 to pi. Then you got to subtract the integral of v du, which in this case is 1 over n sine of nx. My du is 2x dx, right? 0 to pi. What happens to this? Gleefully nothing. That is gone. Sine of 0 is 0. Sine of multiples of pi, 0. Gone. So what we do have is 2 over n pi with a minus, integral from 0 to pi. Let me bring that 2 out. 4. And what do I got? I've got sine, excuse me, let me write it this way. X sine of nx dx. All right. Do be critical of me if I make a mistake here. Okay, so continuing, we integrate by parts again. Here's my dv2, here's my u2. We get minus 4 over n pi minus x over n cosine of n x, because the integral of sine is minus cosine like that, and then plus the integral from 0 to pi. Of course, that has to be evaluated from 0 to pi. Integral from 0 to pi of 1 over n cosine of nx dx. All right, so let's get it done. Minus 4 over n pi. Plugging in 0 gives me nothing, but plugging in pi gives me something. Minus pi over n cosine of n pi plus what? 1 over n squared sine of nx evaluated from 0 to pi, which gives me nothing. So in short, we have pi's cancel, and we get 4 times minus 1 to the n over n squared. So let me put it all together. We have x squared is equal to pi squared over 3 plus the summation n equals 1 to infinity of 4 to the minus 1 to the n over n squared times what? Times the cosine of nx. What happens if we take this formula and put x equals to pi? Put x equal to pi, you get pi squared equals to pi squared over 3 plus what? Sum n equals 1 to infinity. What's cosine of n pi? Cosine of n pi is minus 1 to the n. So you see minus 1 to the n and minus 1 to the n, they multiply together to give me 1. So this kills that, and you're just left with 4 over n squared, which tells me that the summation n equals 1 to infinity of 1 over n squared is actually equal to 2 pi squared over 3, all divided by 4. What's that equal to? What's 2 over 12? It's 1 over 6. That, my friends, is pi squared over 6. And this is probably how Euler knew the sum of the p equals 2 series was pi squared over 6. I don't know of a non-Fourier way to derive this fact. Anyway, there you go. And no, this is not on the test. That would be unfriendly.
Agreed.
So you can complain. I spent a whole class period teaching you something not on the test. Rail against it if you'd like. I don't mind.
I enjoy this.